All right, recording is rolling. So it is Thursday, November 3rd. And yeah, here's what's going on. So you guys know tomorrow you're definitely going to bring those laptops so you guys can do the bear test in class. Now, if there are a couple of guys who don't have your laptop for whatever reason tomorrow, then that'll be all right, because that could be a good opportunity to maybe finish. You can work on the quiz that I gave you guys yesterday. Open Notes take-home quiz. You guys can possibly finish the puzzles if you haven't finished them by this weekend. I'm going to try to knock those out in class today. We'll do as many as we can, hopefully all of them. And then let's see. There's a couple other ideas I want to fill in here before I get to those puzzles today, but then we're gonna take today just to mostly work on those. All right. Here I've got a Friday is going to be a picture retake day. So if you want a picture retake, now they did put out the schedule to try to, I think, pace out different last names during different class periods, just that there wouldn't be like a lot of students all during one class period. You can probably go anytime, but just anyway, this is posted to Google Classroom if you want this name schedule for retake. Also, I posted this to Google Classroom, just a quick checklist of things that are due. So bring your laptop tomorrow for the bear test. I'm giving you guys time in class to do that. But, you can actually do this at home also, but I know I want you guys to spend your time at for physics stuff at home, but focusing on physics stuff. So okay, so you guys remember chapter 5 puzzles are going to be due Monday. We're about to knock those out anyway right now. And then your energy quiz also due Monday. Okay. All right, you guys good there? What's going on? What we're doing? All right. Yeah, go ahead. Okay, so there is a link posted to Google Classroom. You guys remember you made an account? You guys remember the other day when you guys got your laptops? Right. So tomorrow in class, I'm gonna have you guys open your laptops, open that link, and since you've already made your account, or probably almost everybody has, then you'll be past that step. You can just go straight into the bear quiz test. It's for NIMSY. It's not gonna like get you to college. It's just a thing for a program that the school signed up for. So it's just a thing that we're gonna do. Yeah. So I have a multiple choice. I took it myself. Looks all right. It takes about 40 minutes. So yeah. Right. So I'm giving you guys a time in class tomorrow to do that. All right. Right. So there are a couple of energy ideas that I never had time to get around to. So we're going to knock this out now. All right. So one of these is a very classic physics question, which involves a roller coaster. You guys see that, a roller coaster track? Okay. And maybe I could park a roller coaster up here. It starts approximately from rest and then goes around this loop. And do you guys think that right at this point, it's probably most vulnerable to maybe like fall off the track, something like that? Forgot I have a really good video for this too. Let me get this connected, and then I'll switch over in a minute. All right, so after that connects, show you guys this video. All right, and the question goes like this: suppose this track was like really low. Suppose it was like, suppose you started the roller coaster from here, from rest, like from this point, right? Is it going to have enough juice to get around? And the answer is going to be no, because this is sort of related to, do you guys remember filling this with water and going to a vertical circle that was flying around? There was like a minimum speed this has to have at this point to get around the track. You guys remember that? Okay. But if there's a minimum speed it has to have here. So like if you start at equal elevation over here, let's say it would have all potential energy, then it would get more and more kinetic, and then it would go up here, that would turn back into potential, and then would run out of juice at this point, right? So have no speed. So it's fall off the track, everybody dies. Oh, that's bad. So I bet there's like some like minimum height. Do you guys think like a minimum height? Make sure it gets around. So this is going to be like a two-part problem. We're going to go back and revisit how fast does this have to go around at this point, based on the radius of this loop. Okay, and then we'll go an extra step. That's going to be conservation of energy step to figure out what is that minimum height there. Right, so let me do this. I'm going to switch my screen over, show you guys this video real fast so you guys can get a good visual on this. All right. And now they went with the bowling ball, which doesn't involve rolling physics, so we're going to kind of ignore that. But okay, so it's at the top of this loop. No, all right, and let it go. Look at that. And that guy wearing the helmet, he ends up being okay. He's okay. Yeah, look at that. But probably like right there. Right. That bowling ball better have some speed so it doesn't like fall down and clunk. Right. All right, so switch back over and let's solve this problem. Does anybody happen to remember what the minimum speed is at this point in terms of the gravity of the planet and the radius of this loop? Does anybody remember? V min equals what? It's like a square root expression. You guys remember that? Okay, well, let's go solve that then. All right, so I'm thinking that to stay on this dashed line curved path, this some radius r, right? If I make a free body diagram, there's one or two forces acting on this roller coaster at this point. There's its weight, of course, mg, and there may or may not be a normal force from the track. There probably is. I'll call it F sub n, right? But what if the roller coaster just barely gets around? What's that normal force go to? 0, right? So what I'm doing right now is definitely a skill that you guys should be able to have by May. Okay. So if you let that go to 0, then I could say that the centripetal force is provided only by the gravity force. I would normally say plus the normal force also, but that just goes to 0. So centripetal force, is that called mv squared over r? And gravity force, is that called mg? Right? You guys can do that? The mass cancels out. If you solve for v, do a little algebra switch around. Is it square root gr? Right? That's at least the third or fourth time you guys have seen that in this class at this point. Right? So for this particular problem, how fast I have to go around, make around the loop, square root gr. Okay? Okay. All right, so that's part 1. Now let's go do the energy conservation part, because again, there's some minimum height. I'll call this h min, right, to guarantee that it gets around. And we're going to solve this in terms of variables, because there's a very interesting solution actually just in terms of variables. Okay? So can I do sum of energy initial equals sum of energy final? Here's initial, here's final, right? Point A to point B, point, is that true? Okay. So at the top, it's all potential energy, right? MGH. Okay. And by the time it gets to point B, let's see, it's actually not at the lowest point. There is potential energy here, right? You guys see that? Here, guys, what is the height of the roller coaster at the final location? Is it 2r, right? Wouldn't that be the diameter of the circle, and the height would be 2 times radius? You guys see that? Is that okay? So there's a mix of potential and kinetic here. Okay? So some of the energy went into lifting it to that point, and whatever's left over goes into kinetic energy and gives it a speed. Just like that, right? Is that true? But you guys know the minimum target speed. So can I take this expression and pop it in right here? Right. Square root gr can go right there. That's like the bare minimum you want to have, right? Is that true? Right? All right, so let's clean this up a bit. I got mgh goes to, I'll just slide this 2 out in front, 2 mgr plus 1/2 m, and let's see, v squared, square root of gr squared, isn't that just like gr? That okay? Okay. Hey, look, 2 of something plus 1/2 of something. 2 mgr plus 1/2 mgr. Is that like 2.5 mgr? It's like 5/2 mgr. Okay. So mgh turns into 5/2 of mgr. Right? Right. No, we're not quite done yet, but we're getting close. Okay. Guys, what cancels out both sides? The mass and the gravity field. Whoa. So not only does it matter, not only does it not matter if there's passengers in the coaster or not, but also you could take this to a different planet and you would still get the same solution. And the solution's right here. Height minimum is 5/2 radius, or you can also call it 2.5 times the radius. 2.5 times the radius of the loop. Okay. Now we're assuming, of course, no frictional losses and no energy that goes into rotation and the whole deal, right? But okay, there you go. You guys get it? It's a very classic physics question. You guys take physics in college, you'll like 99% chance you're going to see this problem, and a decent chance you'll see it on the actual AP exam too. Right. The other one I wanted to cover with you guys goes back to the conservation of energy packet. There's, well, I guess it's conservation of energy packet. Okay. Now it involved these 2 asteroids gravitating close to each other. I think we did address this in class, but there's one more step I want to take this. Right. So I told you guys this whole story of like why, from a universal sense, potential energy is negative GMM over R. If they're two objects like infinitely far away, there'd be zero potential or kinetic energy. Right? It went through that whole story. Okay. And then if something crash lands from the edge of space, it'd have a speed. If something crash lands from the edge of space, the speed of that crash you get for conservation of energy instead of being square root 2 GM on R, which then if you turn around and throw it straight up in the air and you want it to escape gravity of the planet, would also represent the escape speed. Right? So we already went through that part of the story. That's in your notes from a few days back. But I want to take this a different way. I want to show you guys why negative GMM over R for potential energy also simplifies to MGH, localized to the surface of a planet. Remember, we got these two different perspectives on potential energy. We almost always use this one, localized to the surface of a planet. But remember that lowercase g changes, it's supposed to when it's in a rocket to the moon, so you have to use the universal form. But I want to show you guys this actually simplifies to this. Okay. It's a good skill to be able to have to do something like that. Right? Yeah. Nothing to do with the skates. Okay. So, right. Suppose there's a planet and has a big old mountain on it, right? Like Mount Everest, right? Except my picture is nowhere even close to scale. Mount Everest would be nowhere near that tall if my if this were actual Earth. Right? I'm gonna call this radius 1 and radius 2. You see, radius 1 goes to like sea level and radius 2 goes to the top of the mountain. That's it, right? But they're almost the same thing. Like R1 is approximately equal to R2, but they're not exactly the same, but they're really, really close, right? Which is basically true, right? If the Earth was the size of a bowling ball, it would actually be smoother than the bowling ball. It's like so close to a sphere. Right. So I want to say, do you guys see the difference between R1 and R2? I might call H like a height change. You see it? Okay, so I can say this R2 minus R1 is equal to some height change. Okay. Right. And what would happen if I take the difference in potential energies between this point and this point? And I'll start from the universal form, which is like the more globally true form. So the difference in potential energy, we'll call it delta U, difference in potential energy, is see negative G M M over R2 minus negative G M M over R1. Okay. Capital M is the mass of the planet. Lowercase m could be the mass of like, I don't know, just some object at the surface, right? Okay. So you got difference in potential energy. Okay. Now, hey, could I get a common denominator for these by multiplying this guy by, let's see, negative G M M over R2, multiplying this guy by R1 over R1, and then minus negative, that just turned to plus. G M M over R1, multiply this guy by R2 over R2. All I'm doing is just very simply getting a common denominator. You guys see that? Okay. So now I get this fraction, this fraction. Okay. I'm going to swap both sides just to have plus and minus the. So delta U equals GMMR2, and then minus GMMR1. This is all over R1, R2. Just like that. In that picture? Okay. Oh, okay. I can factor out the GMM, right? The GMM bit. So delta U is, okay. Let me do one more little shuffle while I'm at it. I'm going to take that little m and just bring it all the way to the front. And this makes sense in a minute if I'm doing this. Okay. And then this is going to be, I've got a G, I've got an M, I've got an R1, R2 down here, and I've got an R2 minus R1 here. Okay. Is that? Now, capital G, capital M over R squared. Because remember, R1, R2 are they're so close to each other here. Isn't this basically GM over R squared? Isn't that just lowercase g, gravity field of a planet? So change of potential energy is the mass of the object times gravity field of the planet times R2 minus R1 is the height change, MGH. Boom, there you go. That's how you derive MGH. Okay. Guys good? All right. Right, so yeah, all the little details I want to fit in here. Good stuff to, I mean, you really got to like sit down and think deeply about this stuff and have time with it, but trying to make the most of today here. All right, so jump into these. Oh, so circle all the ones I assigned you guys. Let's see if we can do all of them possibly. So number one, a weightlifter lifts a set of weights from the ground. They told you how much it weighs in newtons, so they gave you the weight. That's fine. To a vertical distance of so many meters. How much work did the weightlifter do, assuming let's say constant speed? So all you do is work equals force times distance, right? If you made a free body diagram, you guys know that the weight and the lifting force would be the same, right? It looks at constant speed. Right? So you just plug in that number, the distance is the height, plug in, boom, done. You just plug in the numbers, right? You guys can do that? Okay. So you just multiply the two numbers they give you, the weight and the height. Weight times height. Okay. Number 4, the shopper at supermarket pushes a cart with so many newtons force directed at an angle so many degrees below the horizontal. Is just sufficient to overcome various frictional forces so the cart moves at constant speed. Okay, this is really similar stuff to one in the notes back in the day. You guys remember cart? Okay, so let's get by a diagram going on this guy. Okay. There's the applied force, the pushing force, that's so many degrees below. Let it go, 35 newtons. Okay, this cart has a weight. Mg, right? And there should be like a huge normal force. Notice I made the normal force greater than the weight. Like I said. Okay. Did they say? Okay, I don't think there's enough information to figure out those. Right? But there is. They did say the cart goes at constant speed. So wouldn't that be? Wouldn't it be the case that the frictional force has to balance out with the forward component of the pushing force? Is that true? Okay. So how much is this actually pushing forward? Maybe I'll like dash the component right here. Okay. Wouldn't this component here be 35 newtons times cosine of 25 degrees? Is it? Okay. And then the friction force just be exactly the same magnitude, just opposite direction. Right? Because there's zero net force, because there's no acceleration, constant velocity. Right? Like I said. Right. Right. What were the questions? Find the work done by the shopper. So work is force times distance. Okay. So I'm looking at 35 newtons cosine 25 degrees times the distance of 50 meters. So 35 newtons cosine 25 degrees, 50 meters. You guys can multiply that in your calculator, get some number of joules, right? You guys can do that. There's a follow-up question. What is the net work done on the car? Okay. Guys, if this car's not going up any hills, there's no elevation change. There's no change in potential energy. But also the car's going constant speed, which means there's no change in kinetic energy either. So what's the net change in energy for the car? 0, right? But hang on, I thought we were doing like all this work, all this number of joules of work on the car, right? Over 35 cosine 25 degrees times 50 meters. What's that? 1586? Are you guys getting 1586 joules? Something like that. Okay. Wouldn't the work be done by friction be equal to negative 1586 joules then? Because whatever work you're putting into it, the friction force is doing exactly the negative of that force times the same distance, which it's a wash. So work net equals 0 joules, right? Which is the work you do plus the work by friction. Add those up. There's 0 net force, or sorry, 0 net work, I should say. Well, I guess both are true. 0 net force and 0 net work. Okay. Guys good? Right, number 5. Starting from rest, a 5 kilogram block slides down 2.5 meter incline, 30 degrees. It is rough, so there's friction. Coefficient of kinetic friction is this number 0.436. Okay. Call it 43.6%. The normal force. The work done by gravity, the work done by the friction force between the block and the incline, the work done by the normal force. Right. So, yeah, we're on number 5. Number 5. Okay. So here, let me do this. Yeah, I think we're right. Okay, we've got 30-degree incline, 30 degrees right there. Okay, we got a block. Actually, let me put the block out here so I can get a better diagram. Okay. I'm going to introduce a Cartesian system that runs parallel perpendicular to the surface. That's a really common thing that we avoid to do. Let's get some forces on this thing. So we're gonna have the weight mg. Now, they said 5 kilogram block, so can I call that weight of about 50 newtons? Right. Is that right? 50 newton weight. 5 kilograms, 50 newton weight. Oh. There's a normal force of, wouldn't the normal force be 50 newtons times cosine of 30 degrees? I mean, you guys have done so many of these by this point. You guys see that 50 newtons, you can, here's 30 degrees again. Here's cosine of the cosine component, which is equal to that. That would have to be true, right? 50 cosine 30 degrees. Okay, like this happens to be 43.3 newtons. Okay. Now there is a rough incline, so we've got a friction force acting this way. Force due to friction. Okay. Now, I had to get the normal force before I could get the friction force because they told us what coefficient of friction was. So friction force is equal to the coefficient of friction times normal force. Okay. Normal force is 43.3 newtons. We just figured that out right there. And they told us coefficient of friction was 0.436. 436. So very precise value. So that times 0.436. Okay. I'm looking at 18.9 newtons, let's call it. Okay. So friction force is 18.9 newtons. Okay. Right there. Question A, what's the work done by the force of gravity? Oh, and they also said the distance moved is like 2.5 meters. Maybe I'll switch the ink color to show a distance. So let's say this distance is 2.5 meters, 2.50 meters. Okay. Now, the work done by gravity, that's the gravitational force times the distance times, I know I've been saying cosine of the angle between them, but wouldn't the cosine of the angle actually be the 60-degree angle right here? Okay. So you could go the full weight 50 newtons times the full distance of 2.5 meters, right? Either times cosine of 60 degrees or sine of 30 degrees. Okay, so the work done by gravity is 62.5 joules I'm looking at. Okay. The other way you could do that is you could just do mgh, right? You guys see a height change of 2.5 meters times sine of 30 degrees, right? You guys see a geometry triangle right here? Okay. So 2.5 meters times sine of 30 degrees is the height change. 2.5 meters times sine of 30 degrees. Height change is 1.25 meters. Okay. And then if you do mgh, right? So mg is 50 newtons. Height is 1.25 meters. It's still 62.5 joules. Okay. So the work done by gravity is so the work done by gravity is 62.5 joules. Okay. There's two different ways to get there. Part B, the work done by the friction force. Work done by friction force. Right. Well, wouldn't that be this force times this distance? And notice that they're exactly opposite of each other. So, guys, what's cosine of 180 degrees? -1. Ah, okay. So isn't friction like doing negative work then on the block? Okay. So we're going to go force times distance, 18.9 newtons, 2.5 meters, and cosine of 180 degrees, which is just going to make it negative. So 18.9 newtons, 2.5 meters. I'm looking at 47.25 joules. How about that? Just round a little bit. 47% joules. Okay. It's done by friction. Oh, whoop, and it's negative. Oops, it's negative. Okay. So it's doing negative work on the block. Like it's trying to slow it down. Question C. The work done by the normal force. Okay. This is kind of a conceptual question. Guys, remember how work is the dot product of force and distance? You need the same, but you need parallel components. But guys, isn't the motion of the block parallel to the surface always perpendicular to the normal force, which is perpendicular to the surface? Right. So sort of by definition, a block sliding along the surface, how much work will the normal force ever do on that block? Zero joules. 0 joules. Okay. The normal force only does work in a case like if there's like an elevator like pushing it up or something. But if it's sliding along, the answer is just 0. Work done by the normal force is just 0 joules. Okay. And question D, qualitatively, how would the answers change if a shorter ramp at a steeper angle were used? Right, so if you take this 30-degree angle and ramp it up, right? So let's think about the big picture process, right? So as this angle is approaching closer to a vertical wall, what's happening to the normal force? Less and less and less, right? And if the normal force is getting less, and the coefficient of friction doesn't change, that's a material property. What's happening to the friction force? Also getting smaller, 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 right? Now, if the total height change ends up being the same, do they specify that? Yeah, they did say the same vertical height, So they're saying like a shorter overall ramp distance, but the same vertical height change. Guys, if the same vertical height change, does the work done by gravity change? No, it's exactly the same, right? I calculated this for you guys 2 different ways, but either way, it'd still be 62.5 joules, right? But what about the work done by friction? What's going to happen to that? It's going to be less, isn't it? Right? Actually, for 2 reasons. Not only is the friction force itself getting smaller as the normal force gets smaller as this angle goes up, but also the physical distance that friction force acts over is going to be less for same height change but a greater angle. Right? So for both those reasons, there's going to be less work done by friction. Well, less negative work, I should say, right? Closer to 0 joules of work. Right? And then the normal force would still be 0 joules of work. Okay, you guys got that? That right there is actually a really good AP style question. I could totally see it being a multiple choice question from AP. They could ask something like that. Any of the questions that we just covered. Okay. All right, guys, good. All right, number 24. Ooh, look at this. We got an Atwoody looking setup. We got a spring. This looks so exciting. 2 blocks connected by a light string, passed over a frictionless pulley. M1 is greater than M2. If the system is released from rest, and the spring was initially not stretched but compressed, find an expression for maximum displacement, M2. Okay. Now I should tell you guys, maximum displacement and the final equilibrium location are going to be different questions. If they ask like if this oscillates for like a few minutes and eventually comes to rest, and they said like how much is the spring stretch, you would actually go back to unit 2 dynamics and you set up in equilibrium with forces. Right? So you say all the forces balance. Right? That's not what we're going to do here. We're looking for the maximum stretch. It's going to like overshoot the equilibrium and eventually, right? So the maximum stretch point, right? We're going to go, let's set up a conservation of energy. So if you see like springs, they ask for equilibrium, do forces. If they say what's like the maximum stretch, set up conservation of energy. So sum of energy initial equals sum of energy final. Okay. Now in the initial state, they said the spring wasn't stretched or compressed, so there's no energy in the spring. Okay. But I do see that this M1 can like fall down, right? The M1 can fall down. So isn't that providing potential energy? M1GH, right? And that H is like the height that it can fall, right? And let's say as low as it goes, we'll call that height 0. So this is this actually is like what we're solving for, right? The height change of block 1 as it falls, because block 2 is going to be lifted that height, and the spring is also going to be stretched that exact same amount, isn't it? Right. So I'll say equals. Now, where would that energy have gone? I'm thinking 2 places it's gone. One is into lifting block 2, M2GH. Yeah, same height. And the other place is in stretching the spring, 1/2 kx squared. But instead of x, I'm just going to go ahead and substitute h. Right? Wouldn't that be the case? Because it's the same distance, right? Wherever distance the blocks moves, it's the same. The spring gets stretched. Wouldn't that be true? All right. So it's 24. Just want to check my work, make sure it is. Yeah. Distance. Okay. Yeah. So we're good. We're good. All right. So then, if you're solving for h, then it looks like one of the h's is going to cancel, right? So let me subtract this over. I've got 1/2 kh. I canceled one of the h's is equal to m1g minus m2g, just like that. True. Okay. And then times 2 divided by k. Okay, we sure got that's the same thing. Looking at my pre-written solutions. Okay, my pre-written solutions, they look a little bit nicer handwriting. Also, I did a little bit overkill on this one. I solved it a little bit different way. So if you want to see a little bit different thought process, then that's what you guys got the solutions for. Okay, there's usually different ways to go about and solve these things, but I got the same answer as I got there. Yeah, it's the same thing. So there you go. That is the maximum height fall of the big block, the maximum height increase of the small block, and also the maximum stretch of the spring because they're all the same distance. They're just that distance right there. Okay. Guys good? All right, next one. 25. Daredevil on a motorcycle. Okay, so they're telling you he's leaving this ramp at this speed. Notice they didn't actually tell you what the angle of the ramp was. That's interesting. Okay. But they did grab a second speed, and that's at the top of this path here. Of course, it's a little bit slower. 35 meters per second, 33 meters per second. It's going to slow down a little bit as it's going upwards. Okay. And the question is, what's the maximum height for this guy? Ignoring air driving deal. Okay. Now, you sort of had a different approach. This is a projectile, isn't it? Projectile. You could actually use projectile physics to solve this. It'd be a long, complicated problem, but you could do it. But with conservation of energy, you can pop, get really fast. Because all you do, just set up a conservation of energy equation. It's really easy to solve. So sum of energy initial equals sum of energy final. I mean, you guys seen this at least 20 times now. Okay, this has been the start, like so many problems in the last week and a half. Okay. So he has all what kind of energy here? Kinetic. It's all 1/2 mv squared. I'll throw a little subscript not on the d, say initial plus. Okay. Now at the top of his path, okay, he's gained some height. So some energy went into his height, mgh. Okay. And actually, that is the question. What is the maximum height he goes to? Okay. And whatever's left over goes into kinetic energy, 1/2 mv squared. But it's like we'll subscript f on it because these are two different speeds, right? Okay. This one's slower than this one. Okay. All right. So yeah, notice they did not give you the mass of the guy, but that's okay because it cancels out anyway, right? Boink, boink, boink. They did not give you the gravity field, but I've only ever seen motorcycles on Earth, so I have a pretty good guess what G is. And can you guys just do some algebra and solve for H? Okay. Oh, let's do terms of variables. That sounds fun. Here, I'll multiply everything by 2. Multiply everything by 2. Boom. All right. So subtract the V final over. So 2GH is V initial squared minus V final squared. Right? Then divide both sides by 2G. So there's the answer in terms of variables. You can plug in any speeds. You could even change planets if you wanted to with this expression, right? Okay. But they gave you that speed was 35 meters per second. That speed was 33 meters per second. There's about 10 meters per second squared. Boom, boom, boom. You guys can solve for that, right? Okay, see that? All right. Number 38. Oh, we're back to an Atwood, classic looking Atwood. 2 blocks connected by light string. There's no springs. There's a string. Over a frictionless pulley, system released from rest. Okay, so M1's greater than M2. It's going to plunk like that. They gave you some values for these blocks. Find the speed of M1 as it's crashing into the floor. Okay. So part A is just find a general expression. Part B is they gave you some actual numbers so you can plug stuff in. Okay. Again, you could have solved this before we ever got to conservation of energy. And the way you have done it is you have to first solve for what is the acceleration of the system. Could you guys take the difference in weights divided by the sum of the masses, get the acceleration? This is accelerating down, this is accelerating up. Okay. Then you could say, well, if I know the height change, I can go back to this third kinematic equation. No, goes back to unit 1. Say if it starts from rest, boom, that goes away. Here's the height change. Here's the acceleration you would have solved for based on the properties of the Atwood, and then you could get crash speed that way. Okay. Now that's like a multi-part process to solve it that way. Dynamics followed by kinematics. But we have a faster way to solve this now. We're just going to use conservation of energy. Okay. Of course, either way you do it, you're going to get the same answer, right? Different paths through the force to get to same solution. Right. So here you go, sum of energy initial equals sum of energy final. Okay. Where the initial energy is the fact that the large block can fall is not going to provide all the potential energy. It's going to fall. And that energy is going to go into 3 places. Actually, I think this might have been one of the ones we did on a 3-page table, right? What's one of the 3 places? What's one of the places the energy goes to? You have to lift block 2, right? Is some energy going to go into lifting block 2? Right? The same height, right? One falls, one rises. And then whatever energy is left over goes into kinetic energy for each block. There's a 1/2 m1 v squared plus a 1/2 m2 v squared. Is that true? Right. And the question is, what is this v? Right? Is that true? Right. Good. So I'm gonna here, I'll take all my kinetics on one side. I'll factor out the v squared while I'm at it. So I'm putting a few algebra steps together. Right, then let's take this term, subtract it over. So m1 gh minus m2 gh. Okay, right, so give me a couple of other algebra steps in between, but at some point you'll get that expression. Okay. I can multiply by 2, divide by the sum of masses, take the square root. Right, so v is, let's see, multiply this by 2 times, oh, you know what, I can factor out gh while I'm at it. m1 is minus m2 gh. Okay, so multiply by 2. I'm going to divide by the sum of masses. And then finally take the square root. Boom, 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 just like that. Okay. What's that, number 38? Let me check my answer. Just make sure I'm not lying to you guys. Yeah, that's exactly what I got in my solutions. Yeah, all right. So you guys got that? And then part B is just plug in numbers and just get a specific answer for some specific set of blocks. Okay. You guys good? Okay. Number 53. The electric motor of a model train. Model train accelerates the train from rest to this many meters per second in 0.21 milliseconds. You guys see there's going to be a conversion going on here? It's milli, is that 1/1000? So this is 21 over 1,000 seconds, right? The total mass of the train is so many grams. Grams. Do you think you're going to have to convert to kilograms? 800 grams, is that 0.8 kilograms, right? 3 decimal places. Find the average power. Right? Now, I did give you guys 2 different ways to find power. The sort of definitional way is the rate of energy, the rate of work, which is actually the faster way to do this one. Okay. So power is equal to work over time, right? Which is the way I'm going to set up and solve this. Okay. But sometimes here, do you guys, who remembers what is an alternate form for power that involves like a force and a speed? Does everybody remember? Okay. Force and velocity. Yeah. Leonardo remembers. Okay. You guys remember too? Okay. Because guys, isn't work force times distance? And if you do force times distance over time, hey, distance over time could be velocity. So force times velocity, it's the same thing, right? Okay. So sometimes this is helpful. I'm going to do it this way for this one. Okay. So from rest to some speed and some time, that sounds kinematic. That sounds like damn it. Over time grams. Okay. Oh, you know what? You know what? Actually, I thought of a better way to do this. That actually involves this section. Okay. If it goes from rest means it had no initial mechanical energy. Okay. And if it goes to some speed, then wouldn't that be give it a final kinetic energy? Wouldn't the work done on the train all translate into its kinetic energy? Right. So the power, I'm just going to say, is the final kinetic energy, 1/2 mv squared of the train. Right. No, that's just the work done. Right. And then this all happens in some time interval. Right. Just like that. Okay. Here's we're going to plug in stuff. Right. So the mass of the train was 875 grams. So be divided by 1,000 for kilograms. 875 over 1,000 kilograms. Right. Then the final speed of the train was 0.62 meters per second, 0.620 meters per second. Square that. Right. So there's the final kinetic energy of the train, which of course is the work done on it. It's a flat track, no friction. And then this all happened in, because you're saying no frictional loss is what I should have said. Okay. 21 over 1,000 seconds. It should be like that. Okay. Here, let's solve this one with you guys. 1/2 times 875 on 1,000, 0.62 squared, all divided by 21 on 1,000. Right, so it's a little bit of conversions going on there. Right, I'm getting 8.01. Guys, what unit would this be? Eight what? Power. What do you see stamped on a light bulb? Watts, right? Right, I was always gonna write joules, but it's joules per second, which is watts. 8.01 watts. Right, capital W stands for watts in that context. Right, that was number 53. Right, let me check my work. Yeah, that's exactly what I got my solutions to. Okay. 8.01 watts. Okay. All right, guys got that? Okay. Again, that's just one way to solve it. There's other ways you could go about it too, but. All right, number 60. Number 60. Oh, do you guys see a force versus distance graph? Force versus distance. You know what? I want to make a whole deal about this. Okay. You guys remember on the very first day of school, I gave you guys these 3 papers that were stapled together. Okay. One of these is your AP equations that you can also use on the actual exam. One of these is all the variables and units that we're going to be using in this class. And I gave you guys some examples and some notes on those. Okay. And one of them is this page where you go section by section. I gave you all the here the key flag where you would know to use that particular unit, some formulas, some examples, and some graphs. Okay. And here, definitely be familiar with those. Energy, under energy, this is the graph I gave you. Notice it's force versus displacement, F versus X. Get that? F versus X. Okay. And see how the area under that represents the work done. Okay. That's something you're going to want to know. Now, next week and the week after, we're going to get into collision physics, which involves momentum and conservation of momentum. Okay. And there's a very similar looking graph, but it's different axes. There's force versus time, and the area under that represents a change in momentum. Right. So force versus X, force versus T. Right. Different concepts, different units. Right. Okay. But the area under that would represent how much work was done. Okay. Right. So that is exactly what we got going on right here. Okay. Force versus distance graph. Object mass so many kilograms subject to a force. No, it's a variable force. Notice it's not a constant force. If it was a constant force, this would just be a rectangle. You just go work equals force times distance, call it a day. Base times height for a rectangle. But it's like a trapezoid shape. Okay. So find the work done on the object as it moves from 0 to 5 meters. Now 0 to 5 meters. 5 meters is just this initial triangle, looks like, right? You guys see a triangle right there? And then from 5 to 10 meters. Right, and then from 10 to 15 meters, right? So the triangle followed by this middle rectangle followed by this final triangle. Okay. They ask for the work done on each of those sections. If the object has an initial speed to start with, so it wasn't even at rest to start with, but that's okay. We'll address that later. Okay. Find the speed at the at different locations. Okay. Right. So number 60. Maybe I'll call those here. So 0 to 5, t equals 0 seconds to t equals 5 seconds. Okay. Shouldn't that be 1/2 times base times height because it's a triangle? 1/2 base height because it's a triangle on the F versus X graph. Here, maybe I'll just call it section A. Okay, so work on section A, section B, section C. Okay. So 1/2, we've got a base of 5 meters. Or I'm so sorry, I messed up this subscript. It's not time. I just made a whole deal about that. It's distance. X equals 0 meters to X equals 5 meters. Oops. Otherwise, we would have been talking about momentum. Oops. Okay. So changing the location here. 0 to 5 meters. So I got a 5 meter base, and I've got a 3 Newton height on that triangle. Okay, and it's 1/2 base height because it's a triangle, right? So 1/2, 5, 3. Okay, looking at 7.5 joules of work done just during that first section. Okay, then there's that middle rectangle, which is just going to be base times height because it's a rectangle. Guys, 5 meters to 10 meters. Is that still a 5 meter difference? Okay, 10 meters minus 5 meters base. And then the height is still 3 newtons. Oops, 3 newtons. 3 Newton height. So 5 times 3 is like 15 joules. 15 joules of work in that section. And then the last section, work on part C, is that an identical triangle just mirrored? So can I just call it 7.5 joules again? Because it looks identical to the original triangle. Okay, right, guess that. If the object had an initial speed of 0.5 meters per second at x equals 0, then find its speed at the 5 meter mark and also at the 15 meter mark. Okay, here, I'm just going to solve the last one with you guys, 15 meters after this whole thing. So do you guys see a total of 30 joules? Work total is 30 joules. You guys see that? 30 joules of work that's been done. You guys see that? Okay. So here's where I'm going to treat this as an open system. I mean, it is an open system, right? There's work being done on this object. Okay. And I'm going to say the sum of energy initial plus the work equals sum of energy final. Isn't that an open system? Right. And the initial energy is all kinetic, 1/2 mv squared plus work equals, and then 1/2 mv final squared. Right. As long as it's a level track, it all goes into its motion. Okay. So you can say 1/2 times the mass was 3 kilograms times the initial speed was 0.5 meters, then square that, plus 30 joules of work equals 1/2 times 3 kilograms times V final squared. Okay. Can you guys do the algebra and solve that? Okay. And more importantly, the reason I'm doing this class today is to guide you guys through the thought process. So that when you're looking at the solution, it's like, oh yeah, I remember said this, and this is why this is. Okay. Right. I think I'll have time to at least look at this one here because we got 2 minutes. Okay. Number 37, Tarzan. Swinging on a vine. So we got a pendulum situation. Here's Tarzan swinging. They told you the length of the pendulum was so many meters. They told you the starting angle was so many degrees. And they said, what's the speed at the bottom? Oh, it's V bottom. Right. For 2 different situations. One is if he starts from rest, but the other is if he kicks off with an initial speed. Okay. So cut through the geometry. You guys remember this is L times cosine of theta. And this height change, which you really care about for your equations, is L minus that. You get factor out in L minus 1 minus cosine theta. We went through this before. That look familiar right there? You guys remember that? Okay. All right, now here's the 2 ways to set this up. Part A, you could do sum of energy initial equals sum of energy final. He starts off with all mgh, but that h is L1 minus cosine theta. And he ends up with all 1/2 mv squared. The m cancels. Can you guys solve for v? Okay. And question B is he pushes off. Now, it'd be really tempting to just take your answer from A and just add the original speed, but that doesn't work. That didn't work. That's a really common misconception. What you have to do is this. You have to say 1/2 mv naught squared plus the mgh equals 1/2 mv final squared. And you actually get a different answer this way, but this is the correct way to do it. This is the correct way to do it. Okay. Great. And Billy's all right, I think you guys are good because we hit all of them except for one, but again, you guys have to sleep in. Right. This is something you want to sit down with, really think deeply about, and I'll pick these up from you guys on Monday. Okay. Along with taking quiz. All right, you guys have a great Thursday, and remember tomorrow, bring your laptop for the bear test. Oh yeah, bear.